So we're going to talk about dilations today, and in the last unit we were talking about rigid motions. Transformations, transformations that do not change the size or the shape of the figure. And the transformations that we use were translation, which means that we move the graph right or left, up or down. And then we did a rotation. We moved it from one location to another, and we also did reflections. We did reflection second, where we flipped the graph over some line of reflection. And then we're going to talk about the dilations now, the new type of transformation called a dilation. And if you think of getting your pupils dilated, that makes the pupils bigger. And in math, dilations, we can make the figure bigger or we can make it smaller. We still don't change the shape. And the thing is that a dilation, because it does change the size, is not a rigid motion. What's something that's really important that might seem obscure is the next sentence. It says, rigid motions create figures that are congruent. All corresponding angles and sides are the same, meaning that when we do a rigid motion, when we do a translation, when we do a reflection, when we do a rotation, we still have a congruent figure. When we do a dilation, we do not. So in the case of just a translation, again, translation meaning we move the graph right, left, up, or down. It's a rigid motion. What we know about these two figures is that angle G is congruent to angle G prime. And we know the other two as well. Angle T is congruent to angle T prime. And angle B is congruent to angle B prime. And it's the same idea for the sides. And you don't have to have these listed in the same order, you just have to have them listed. So in this case, segment GT is congruent to segment G prime T prime. And segment GB is congruent to segment G prime B prime. And segment BT is congruent to segment B prime T prime. Again, that's with a rigid motion. That could work with a reflection as well. That could work with a rotation also. Dilation creates figures that are similar. And what happens with regard to similar figures are they create angles, corresponding angles are congruent, but corresponding sides are proportional. This means the ratios of corresponding sides are the same, but when performing a dilation, the pre-image and the image will always be similar to each other. They won't be the same length, they'll be proportional to each other. So as we take a look at this one here, as you can see, the figures are still the same shape, but not the same size. So what we know in this particular figure is that angle P is congruent to angle T prime. We also know that angle L is congruent to angle L prime. Angle A is congruent to angle A prime. And angle J is congruent to angle J prime. angles are still congruent with the dilation. It's the sides that have a different symbolism. And what it is that side PL is similar, and the symbol for similar is just one squiggly line. PL is similar to P prime alpha. Again, you don't have to have these in the same order. Side PA is similar to side P prime A prime. Again, one squiggly symbol for the similar. AJ, side AJ, is similar to side A prime J prime. And side JL is similar to side J prime L prime. The ratio of the sides of similar figures is called the scale factor. And we use the scale factor to enlarge or reduce the size of a figure when performing a dilation. When the scale factor is less than 1, the figure will become smaller. So typically it's going to be a fraction or a decimal. When the scale factor is greater than 1, the figure is going to become larger. When asked to transform a figure by dilation, it's sometimes going to be written in sentence form, like dilate the figure by a scale factor of 4. It also can be written in the mapping notation form, which is xy maps to, that's what the arrow means, 4x, so that's the scale factor of 4 for x, and 4y, scale factor of 4 for y in this case, where the scale factor is the number in front of the x and the y. In other words, what you do is when performing a dilation, just multiply all of the vertices by the scale factor. So the first one, write the coordinates of the image of the figure with vertices A, negative 9, 6, B, negative 1, 3, C, 12, 0, D, 3, negative 15, using the transformations xy maps to 1/3 x and 1/3 y. That means that we're going to multiply every value in these ordered pairs by 1/3. And either use your calculator or use Desmos, whichever one works better for you. If you are using a modern graphing calculator, the fraction button is at alpha, y equals, enter. Desmos will be provided on the screen during the test. But if you're using, again, the graphing calculator, it's alpha, y equals, enter. Will give you the fraction button. So you can type in 1/3 times negative 9 is negative 3. 1/3 times 6 is 2. Vertice B. 1/3 times negative 1 is negative 1/3. 3 times 1/3 is 1. Vertice C. 1/3 times 12 is 4. 1/3 times 0 is 0. And vertice D. 1/3 times 3 is 1. 1/3 times negative 15 is negative 5. Another example 1. It says, graph the image of the following figures using the given transformations. Where you've got xy maps to 2x and 2y. So let's look at our figure here. We've got ordered pair F of negative 2, 0. And P is negative 1, negative 1. And V is 1, 2, 2, 2, 2, 2. And we're going to enlarge this time. The last one what we multiply here. Negative 2, 0 becomes negative 4, 0. Negative 2 times 2. 0 times 2 is 0. Negative 1 times 2 is negative 2. Negative 1 times 2 is negative 2. 2 times 2 is 4. 2 times 2 is 4. And we're going to graph our picture. 1, 2, 3, 4. Negative 4, 0. Negative 2. Negative 2. And 4, 4. 1, 2, 3, 4. 1, 2, 3, 4. And we're going to try to draw our picture. And better than usual for me. And what we want to look at here, we want to look at the slope of FV for starters. And I think it's going to be easier for me to get rid of my red for a second so you can see it. I'll put it back in a minute. Don't erase yours unless you really, really want to draw the slopes of everything. But remember, slope is rise over run. So when we look at FV here, we're going to rise 2. We're going to run 4. Rise 2. Run 4. So it's 2 fourths. Or if you prefer, it's 1/2. If we look at the slope of FP, again, remember we draw a triangle. Its slope is rise, except that we went 1 down, and we went 1 to the right. So this is going to be negative 1 over 1, or negative 1 if you prefer. And the slope of PB, again, we rise over run. Go 1, 2, 3 down, and 1, 2, 3 to the left. So it's 3 over 3. It's not negative. We went down 3, which is negative 3. We went left 3, which is negative 3. So technically negative 3 over 3, which is positive 1. And then I'm going to draw that figure back in. That's probably still on your paper. So I drew our picture back in. I'm going to label it. Here's our F prime. Notice that I have point P prime corrected at negative 2, negative 2. And then 4, 4, which is our V prime over here. We want to find the slopes of this particular triangle. And if we look at FB, remember it's rise over run. So we rose 1, 2, 3, 4. And we ran 1, 2, 3, 4, 5, 6, 7, 8. So this one is 4 over 8. If we simplify that fraction, we get 1/2. If we look at FP, F prime, P prime, here is our triangle. We went down 2, to the right 2, down 2, to the right 2. If we simplify that, we get negative 1. And finally, for PV, rise over run. 1, 2, 3, 4, 5, 6 down. And we went left. 1, 2, 3, 4, 5, 6. Well, negative 6 over 6 is 1. And that's something nice to know with regard to dilations. If we look back at this, we see that the slope of FV and F prime V prime are the same. FP and F prime P prime, the slopes are the same. Same thing for PV and its dilated version, the slopes are the same. As long as you don't produce a rotation or a reflection, if you just do the dilation. This means that corresponding sides of pre-image and image will also be parallel to each other. And depending on how well you draw the pictures, you can see it in your picture. But remember that parallel lines have the same slope. For the last two examples, write the equation of the line y equals 6x minus 8 after it's been dilated by a scale factor of 1/2. Well, what did we just learn about slopes and dilations? We just learned that slopes and dilations, we have the same slope. So if we take a quick look at this particular equation, what we see is that the slope of this line, it's already in slope-intercept form, is 6. And the y-intercept happens to be -8. But again, with regard to dilations, dilations have the same slope. So when we write this equation, it's going to be y equals 6x. And what we're going to actually dilate now is the y-intercept. Instead of -8, we're going to take -8 times the dilation, which is 1/2, and half of -8 is -4. Same idea as we look at our last example. Write the slope and the y-intercept of this line. The issue on this one is that we have to put the equation in slope-intercept form. A reminder is that slope-intercept form is y equals mx plus b. But when we look at this here, we're going to solve for y. We're going to subtract 9x from both sides. And we end up with 3y equals -9x plus 5. 3 times y, we need to undo that multiplication by dividing by 3. And when we do, we have our slope-intercept form. -9 divided by 3 is -3x. And you don't need to change that decimal to, or don't need to change that fraction to a decimal. What we know when we dilate here is that dilations are going to have the same slope. So now that we put this equation into slope-intercept form, what we know from here is that our slope is -3. And our y-intercept is the 5/3. Slopes of dilation stay the same. Our slope is going to be -3. If you write -9/3, I'm fine with that. Over here for the y-intercept, as we go back and look at the problem, it says after it is dilated by a scale factor of 6. We need to take this 5/3 and we need to multiply it by 6. And that's when you pull out the decimals, or you pull out the calculator. Again, in terms of a modern calculator, what we do to get the fraction is alpha y equals, and then I'm going to type in the 5/3 times our dilation of 6, which gives us 10, and that's going to be our y-intercept.